Hey everyone, thank you for coming in, and it's a great pleasure to host Sherry today for our talk. Sherry Young is an assistant professor of computer science at NYU and also a staff research scientist at Google DeepMind. She has done a lot of work in machine learning and RL generative modeling, and currently her focus is also on building world models, agents, and their applications in robotics and like AI for science domains. She has been recognized from like she's won a bunch of awards like best paper at iClear, and she's organized a bunch of tutorials, workshops, served as AHS in major ML conferences, CV conferences. She also completed a postdoc at Stanford with Percy and got a PhD from Berkeley under Peter Beal. So without further ado, I'll just try to invite Sherry and learn from her about world models today.
Okay, thank you very much for the introduction. And hi, everyone. Very excited to be here to tell you about world models and agents, but specifically for these high cost environments. So, if we look at some examples of agents and environments, right? Usually, when we talk about agents these days, it's some kind of neural network that interacts with some external environments by taking some actions. And as a result, the environment will return some reward, like how good is this action, and some next state. For example, how did the world change because of this action? So to give you just concrete examples, right? So examples of environments include this, Go game where the actions are where to place the pieces and the rewards are, wins and losses of the game. And in that case, we have already seen that, we can train agents that can outperform humans at the game of Go. And another example of agents and environments is perhaps more recently, we have large language model as agents interacting with some kind of external tools like terminals. And the result of that in this particular case is if the agents can execute code, which is actions in this case, and sees the execution outcome, the agent can try to optimize its code generation, and eventually we can see the agent can achieve superhuman performance in terms of competing in these programming competitions. So given these two examples, I think it's almost fair to say that given high capacity of an agent and a low cost environment with accurate dynamics and reward information, we kind of already figured out how to make agents to achieve superhuman performance, for example, through reinforcement learning, right? And specifically what I mean by high capacity agent is just, large models and deep neural networks, language models. For low cost environments, this is actually something is the key focus of today, because I think this is very difficult to actually achieve for a lot of real world tasks, because the examples we saw where we have superhuman agents, those are in game settings, right? Or in program execution settings where you can just like spin up a bunch of programs and the interactions is really cheap. So because the agent really requires a lot of interactions to learn. So this is probably the bottleneck, right? And so what are some examples when the low cost environment is not true? Well, if you have a physical environment where interaction requires, running the physical robot, this is not cheap at all, because you only have one robot, you can only run one task at a time. And even when we're not talking about physical intelligence, we're talking about virtual intelligence. There are still tasks, even there are still code execution tasks that will be expensive. For example, if we want the agent to do machine learning engineering, the agent will generate some machine learning solutions to train a model for 2 days, and that is not low cost at all, right? Some other examples are if we're doing some kind of scientific experiments, trying to synthesize some novel materials, that is also going to take a very long time. So inspired by these particular three use cases, today's talk, we're going to focus on, trying to come up with some solutions for how to tackle, learning agents in these high cost environments. So firstly, we'll talk about how we can actually train world models using existing data, and then use the world models to overcome the high cost of physical interactions. And then we'll move on to talk about how do we apply and adapt some of the reinforcement learning algorithms for machine learning engineering agents so that they're more amenable to these high cost interactions using language models, which is probably more familiar for this audience. And lastly, we'll talk about, in the scientific setting where we can leverage a system of agents to actually break down tasks and make tasks cheaper and accelerate the tasks, even though, the real experiment is still expensive. So with that, let's start with building world models. So World models is all of a sudden a very popular topic these days, but actually the concept of the world model actually existed a long time ago, way back when people started training these dynamics models on these video game data. And the world model definition is actually pretty straightforward, where you have some observations, for example, previous frames in a game, and you have some actions, which is keyboard controls. You control how you play the game. And then the world model just simply is a dynamics model that predicts the next frames as a result of running these actions in this environment. So as you can see on the left and right, this is models trained in 2018 and 2020. Like these models already look pretty realistic in terms of simulating these game environments. But because these models require a lot of data to train, right? And at the time, only a lot of the games data was available. That's why, the research for world model kind of like stopped there in 2020 and 2018. So I think the interesting question is always to ask ourselves, like, why is world modeling special now, right? Why should we work on this? And I think there are a couple of things. For one, we have actually scalable video generation architectures powered by transformers. And for another, we have internet scale video data beyond just game data, which was used back then, right? So, and I think these are the two key points that makes world modeling interesting. And for that, let's just talk about some of the examples of the video generation architectures. So this is one of the work from NYU where people have developed this called diffusion transformers, where basically it tries to overcome this modeling of high dimensional images by encoding them into some latent space and training an autoregressive model to predict the next latent token and then do diffusion on top of that. And then the predicted tokens are decoded into the observation space. So, and this is probably the most popular video generation architecture today. But because of this transformer backbone, right, we can now all the things that applies to language models now apply to video generation as well, like long context, efficient generations and so on. So this is on the architecture side. And on the data side, I myself have thought more about this. So I started working on this Unisim work in 2023, just thinking about what are all of the available video data that we want to collect if we want to train a world model, right? And so there are a few immediate things that come into mind, because I think world model, the type of data we're interested in is probably different from just a general video generation model. Because for a general video generation model, maybe you want to train on a lot of animations or just for movie creation. But for world model, we're really interested in data of interactions, right? So we sort of looked at what are some of the example data we can collect, and there are a lot of egocentric human videos. And in those cases, oftentimes we have some like task description of what the person is doing. And nowadays, it's not too hard to get these videos from YouTube and label them, right? So there is really like a large source of data. So, and more interestingly, when we train this model on condition on the initial frame and on some high-level text description as actions like cut peppers, and then we train the model to predict these frames, right? So that in some sense, the model has learned kind of like what it means to cut peppers, like how should it look like, right? So this is only one type of data, which is human manipulation. But then, of course, there is a lot of data collected by robots where the actions are slightly different now, because the actions for robots are usually some low-level controls, delta X, delta Y, of where to move its robot endpoints. But nevertheless, we can still train the same model conditioned on the same initial frame and same action space, which is text, but now it's low level text like delta X, delta Y's, and we still try to predict the future frame, right? And just using the same model, we can get the model to model robots as well. And of course, when we talk about robots, then there are a lot of simulation data, right? And what I'm trying to get is that actually each of this data set has its own characteristics. Like, for example, human data has a lot of realistic objects, but they don't have robot actions. And robot actions have robot actions, but robot data has robot actions, but they don't have as diverse of objects, right? And also for simulation data, you have a lot of large quantity, but the quality of the image, they're not very close to real images, right? But the point is, like, if we just feed all of these data into this unified interface, which is this, first frame and action condition video generation model, we can actually get back something that's kind of like a combination of all the pros of different data sets. Just to be complete, right? There are a lot of navigation data as well, so we can give initial frames and some kind of text about navigation controls and try to generate some navigation videos. So Yeah, that's basically it on the architecture and the data side. I just wanted to show you some particular examples, and I think it's probably more fun to do this example interactively. So if you want, you could go to this website, which is universal-simulator.github.io. And then you can kind of get an idea, right? We've been talking about this world models, and you can get an idea of what like an interactive world model might look like. First, a world model being a world model, you should have the freedom to choose which scene you want to interact, right? And if I have the server up and running, you should be able to take a picture of your room and upload it to the server and start to interact with it, right? And second, a world model needs to support diverse interactions. You should give it different language instructions. For example, if you ask a person to wash hands, the person has better wash hands, right? But starting from the same initial frame, you can ask the person to do something else, like pick up the ball instead of washing hands, right? So you can see the person actually following instructions, or ask the person to cut carrots and so on. And the simulator also should support, the world model should also support like repeated interactions. After the first action, washing hands, I'm gonna, shut off water, right? So the person is gonna start from the previous generated video. By the way, yeah, like all of these videos are generated by the model. They don't exist in the actual data. And then again, like manipulation and navigation actually now is captured by the same model, because we can ask a person to turn left. And what we see is, the person turned away from the kitchen and the dining room showed up, which was completely to our surprise, right? Because we couldn't even find like what's the training data for this particular initial frame, because they don't exist. But the model is able to just like purely from a data-driven way, right? Being able to understand, okay, if we turn away from a kitchen, we're likely to be walking into a dining room. And, you can really use language to really structure this world model in whatever way you want by specifying, for example, what happens if we uncover the napkin? We want to have like a toothpaste show up, and we want to have the person interact with the toothpaste in different ways. For example, picking it up or sliding it to a different direction. But you can use the same language. You can control the same model using different language by saying, okay, now we're going to uncover a pen, and we're going to have the person interact with the pen, right? So this is purely data driven. There's nothing telling the model that the distance between the fingers need to be close if it's a pen, and further away if it's a toothpaste. Nothing like that. It's just purely data driven. And you can see that, all of the generations are pretty reasonable. Yeah, so I mean, they're again, like now through video generation, you can generate videos for humans. Of course, you can also generate videos for robots, right? And I will show you more examples of how this is actually useful as a simulator to lower the cost of real world interactions. But the point being, you can really generate many different types of interactions with different initial frames and so on. So that's sort of interesting, right? At least like when I initially saw these results. But then the immediate question is like, how is this useful, right, beyond entertainment purposes? So I think like thinking about how we're going to use the world model is key, because that's going to define the evaluation metrics. That's going to define the direction we should further scale up, where to get data and so on. So the most immediate usage of a world model that came up to me was to use the world model to lower the cost of robot interactions, right? And specifically, we're just focusing on evaluating robot policies. And so if you look at how robot policies are evaluated today, it's basically some PhD students sitting in the lab day in and day out, running one robot at a time, trying to measure success rates. And you got to be robust, so you have to measure things, run the same experiment, same trial 5 times, try to measure some success rate. That's just a time sink, right? High cost. And also, like, if the robot executed something bad and actually smashed its hands into the table, and now you have to wait for a few weeks for the robot to be repaired. That's the safety aspect. And the reproducibility aspect is, I think, one of the reasons that robot learning has been making slower, arbitrarily, arguably slower progress than like language models, is because reproducibility is very difficult for robotics, because if you want to reproduce someone else's policy, you have to run it in the exact same setup, right? Because these policies usually conditioned on the initial frame, right? And if you're running the policy in your lab and then your initial frame, it looks different from someone else who evaluated their policy in their lab, you're likely to not gonna be able to reproduce their results, right? So the initial frame, the environment setup has to be exactly the same, which is really difficult. And on the other hand, what people have thought of is, okay, what about we just evaluate robots in simulation? And these are some examples of the simulations that people use today. And they just look so different from the real world, not just in terms of the visuals, but also in terms of like, simulating physics is hard if you have some soft object, especially. So as a result, usually the performance of the policy in sim versus real, there's not too much of a correlation. So evaluating the policy in sim as a proxy to the real world evaluation is also not very effective. So, because we had the idea of training this world model, right? So we showed a lot of human videos, but in this particular work, which is fairly recent, where we took a lot of robot data, right? So the previous Unisim was only trained on like a couple robot data, but for here, there is actually like a community-based efforts from many different institutions to pull together different robot data sets. And we just took all of these robot data sets from OpenX embodiment, and we trained the same model to condition on the initial frame and some action sequences, and then try to predict the future action sequences. So after we trained the model, we did some quick sanity check, right? So the quick sanity check we did was to move the robot, like program the robot gripper to be moving in a particular direction that we know what should happen, right? So we particularly program the robot arm to just move left and right, which is just masking out the other action dimensions, just keep one of the action dimensions. And we see that roughly, yeah, like the robot does move left or right, up, down, into and out of the page, right? And then closing and opening its gripper, right? And same for different robots. They all seem to be following instructions. So this is the initial kind of like sanity check we did. But I think what's more interesting is, again, you can actually check out a live demo if you go to this website called world-model-eval.github.io. And actually here, by the way, this demo is running in real time. So when you actually select a frame, you're actually passing this frame to the server. And so when you actually press on different keys, like for example, let's press go right. This video is being generated in real time on a few GPUs, right? So let's go right again. And then let's go right and then go down. Let's go down more. Okay, and then let's try to open the gripper. Left, open, open, open. Okay, that took a few tries. Let's open more. And let's see if we can move the robot arm out of the way. Okay, no. All right. Anyways, so you can see like, okay, we try to open the gripper. It tries to grasp this. This is not, it's not perfect, but it's a 600 million parameter model that's trained on 2A100, right? So if you're interested in world modeling, right, it's not some work that has to be done at big frontier labs. You can, the code and data is available. You can go to the website, check out GitHub, start training this model yourself, right? So the point being, right, like this is an example that kind of works well. So you can try to like sweep these beans on the table to different directions. Let's move left again. Move left. Move left. Right. So you can actually, maybe if we open the gripper, see if that works. Okay, that works. All right. So if we lift it up, is it gonna? Okay. Now you can see like, yeah, like the gripper is lifted and then the rod is still on the table, right? So this is actually non-trivial because it's really generalizing to arbitrary initial frames, right? So there are so many frames you can select, and I believe that I have not seen demos like this in the past. It's a small model, it's not perfect, but it is really showing us the way. Okay, so right, so we talked about using the world model to evaluate policies, right? So coming back to that point, so what we can do is we can take these robot policies that people have trained, which is, these policies take some initial frame and it takes some language instruction and it predicts some action sequences. And we're going to give these action sequences to this world model and we generate a few frames. And then we give the last frame of the generated frames back to the policy. And then the policy continues to generate more actions to try to complete some task, right? And afterwards, so this is called policy rollouts. We just roll out this policy in the world model. After the rollouts, we are going to get a full video, right, that is generated by the world model, conditioned on the actions generated by the policy. And we give these video to a VLM, like a ChatGPT, and we ask the model, was this a success or a failure, right? Because the dynamics model itself doesn't have reward information. So we have to use some external reward like GPT to give us the success and failures of these executions. So, but now we have a quantitative metric, right, to compare different policies just by rolling them out in the world model. So here are some examples when we try to roll out different policies. So OpenVLA is like the most recent vision language model fine-tuned on action data. And this is because it's the most recent, we found like it tend to work the best. So this is the rollouts in the world model, where remember, like we're conditioned on one action at a time, right? So the policy is predicting delta X, delta Y. So we're rolling out the policy like 50 steps to actually show, okay, the policy seems to be, completing the task of putting eggplant into the pot. And when we try to like evaluate some older policies, for example, Octo, it tries to grasp the eggplant, but like putting into the pot part is not that successful, right? And then we tried some even older policies. This was from 2-3 years ago, and then the policy just kind of like fails pretty miserably, to the point that it predicted a lot of out of distribution actions that the world model couldn't react properly anymore. But it's pretty obvious from these video rollouts which policies are doing better than the other policies, right? And remember, we didn't run real robot at all, and we are getting an idea of which policy is good. This is some other example. Now we can, not just we can evaluate policies in the world model, we can compare different robots as well, right? So because people are training generalist policies to control many different robots, and now we have generalist world models that can evaluate different robots as well. So here's the example where we just roll out the policy for this particular task, which is to close the bottom drawer. And they all seem to be pretty good at this task, maybe because this task is pretty simple. Right, so those are some qualitative examples. And so we actually also measure the task success quantitatively. So what we did is like we took the numbers from OpenVLA, right? And then we took the initial frame, the real frame from their evaluation settings, because they ran their experiments, they had some real videos. We took the initial frame of their real videos, and then we just input that into the world model, and then condition on the initial input frame for the policy to predict the actions. But then condition on those actions, we predict the future rollouts, right? And then we use the VLM to judge the task success, and then we compute like an overall accuracy. And we found that the difference between this world model simulated accuracy to be really close to the real world accuracy, with only 3% differences, 2 or 3% differences, right, for all of these policies. And then the order between different policies is also preserved, in that RT1 performs the worst and OpenVLA performs the best. So this is very promising. It's telling us, like running real robot for evaluation is, potentially replaceable by just running things in the world model. So I think something that's more intriguing, right, about more than just like reproducing real world results, is to do something creative in the world model by, using tools like Nano Banana. By the way, there's Nano Banana Pro now from Google. I haven't tried it yet. So when we did this is still using the older Nano Banana. But what we did is like, because we can now sort of construct an arbitrary initial frame, right, using Nano Banana. So what we did is we added an orange into this initial frame, and we can create an arbitrary task. So the original task was to grasp the carrots, but here we changed the task to picking up the orange. And like all of the policies fail, right? So we suspect like actually all of the VLA policies are overfitting to their training distribution. We also did something more kind of interesting and adversarial. We put a carrot in the computer screen, and we put a computer screen in the scene, and we try to see, is the robot actually going to pick up the right carrot? And we found the robot really debated in between, the fake carrot and the real carrot, and it decided to pick the fake carrot. And then the world model was also fooled a little bit by, actually showing some changes when the screen was being touched by the robot. I mean, but those are just like illustrations of possibilities that we can experiment with, right, using a world model. There's also something else we were interested in, which is like, we want to understand for these large VLA policies fine-tuned from VLMs, are there different aspects that they're good at? For example, are they good with colors? Are they good with shapes? And then do they preserve internet scale knowledge, such as Taylor Swift and Snoop Dogg, right? So what we found is that these VLA policies are generally pretty good with colors. So when we did things like, so by the way, this initial frame is also constructed. We just took the bridge data set, which is a robotic data set. We just instruct Nano Banana to put either red cloth or a blue cloth on the table. And then we change the task to like pick red. And we found that the policy to reliably select the right color But then they actually are pretty bad with shapes. When we did like the square versus the circle, the policy is pretty random, 50-50 in terms of which direction they would move towards. And we suspect it's probably because a lot of the tasks that people use for robotics, they actually have like language about the color, like, pick up the yellow banana, things like that. But they tend to not talk about the shape. That's why we don't, VLAs tend to not have shape information. And then, when we try to test something about internet scale knowledge, we say pick Taylor Swift. Again, it's pretty random, 50-50 chance which poster the policy will actually select. I think this is revealing something that's more interesting / concerning to the community, which is, remember, these VLA policies are fine-tuned from VLMs, right? And if you were to ask a VLM which one is Taylor Swift, which one is Snoop Dogg, the VLM is probably going to tell you, Taylor Swift is on the left. But, just through this fine-tuning process, we actually lost this information about Taylor Swift and Snoop Dogg. And that's because we're fine-tuning VLM on a very narrow distribution of robot data. Probably in a robot data, there's never Taylor Swift and Snoop Dogg, right? But then it's a question of like, how much data do we have to collect to even be able to come across Taylor Swift and Snoop Dogg and for robots, right? And that's just like almost impossible. So I think this calls into question whether fine-tuning VLMs into VLAs is really the right approach for robots, because we do lose a lot of internet scale knowledge. Okay, so to maybe to maybe just give you more context of what we've been up to. So the World Gym is only doing policy evaluation. Nevertheless, you can really do more interesting things. Now you can roll out the policy, right? Now you have VLM as a reward. You can actually use that information to do policy gradient update to further improve the policy, or you can try to like do some kind of search and planning in this world model to further improve the policy. So even though we mostly focused on evaluation, we have some work on how do we run RL, how do we run search and planning in the world model to improve policy success. So I think the major takeaway maybe from the first part of the talk is that when we have a unified observation space in the form of videos and a unified action space in the form of tokens, whether it's text tokens or action tokens, we can train a unified objective. We can train a unified model using a unified objective, which is just to predict future frames, conditional actions. We get back a very general model. And again, the reason we want to do world modeling is because we can reconfigure the world model in whatever way we want, right? To get these adversarial tests to reveal vulnerabilities of policies. Okay, so that's the first part of the talk. So I know this is an NLP seminar, so I was looking forward to moving on to the second part, which we actually talk about, language models and how do we, make them to do tasks like machine learning engineering. So we're going to switch gears. We're not going to talk about world models anymore, but eventually you will see how things come together. So this particular topic I want to discuss today is like, we want to get LLMs to do something like machine learning engineering. So the particular problem setup is described in this benchmark called MLE bench from OpenAI, where the setup is like this. So you have some data set from Kaggle challenges. For example, the data set has some task associated with it, such as predicting the obesity risk, given these measurements of patient statistics. You have this train and test CSV. So what the agent is asked to do is to come up with some high-level plans. And in this plan, there's oftentimes things like what model to use, for example, where to load the training data, like what is the loss, what is the evaluation metric, and where to store the final outputs for the prediction on the test split. After the high-level plan, the agent is asked to generate some low-level code to implement this machine learning project. And then this code will be executed in some environment, and the execution trace is passed back to the agent. And then the agent can just update its plan and its code and run this in the loop for 24 hours or 10 days. And this is how MLE bench measures performance. The overall goal is to maximize the performance on some held out split like test.csv. So if you look at what the existing work has been doing in ML engineering with agents is mostly through prompting, right? So people develop these very fancy scaffolds, which are basically just collections of prompts organized by Python programs. So for this particular case, this is the state-of-the-art scaffold from MLE, which is called AIDE. And what it does is it basically has a few logics. It has either asks the agent to generate a new solution. For this case, these are the 5 new solutions that it asks the agent to generate, or it could condition on the previous solution and it asks the agent to debug a buggy solution. It could also, and in the background, right, the scaffold actually built this data structure, which is a tree-like structure to keep track of, which node came from which previous buggy program and so on. And there's a third mode, which is to improve a previous solution that was not buggy, right? And then when we run the scaffold for hours, you basically just have this really large tree that have all of your experiment history. And every time the model, continues on to the next generation, it can serialize the scaffold can serialize the history and give this tree information to the agent, right? So this is the setup, the state of the art. And the issue is that when we actually give more compute to the model by letting it run longer, we don't actually see that much performance improvements. So the best solution that's found by the model actually just saturates after 24 hours, no matter how much more time we spend. And so you see, this is pretty far from the gold solution or even human median, right? Which is this dotted line. And I think one of the reasons is that the agent is not actually getting better at this task, right? It's not effectively utilizing these experiences because it's not really learning how to come up with better solutions through gradient updates. Maybe it's doing search, it's just searching for better solutions, but fundamentally it's not learning how to better solve this problem. So what we propose is pretty simple. We're just going to do policy gradient RL, right? Using reward information, which is performance on a test split. But there are a couple of issues we encountered. So, instead of just doing the trace, give the trace back, we also do a gradient update for the policy parameters. So there are some issues we encountered. One being that we actually converge to very fast solutions that finishes executing in a matter of seconds, as opposed to the more optimal solutions. Another issue is that we actually don't make a different distinction between solutions that are almost correct, that just failed at saving test.csv, from solutions that actually failed at importing the packages or loading the data, right? So this is the sparse reward issue. So to actually fix the issue of different actions take a different amount of time to execute, right? So some of the reason that the models just converges to something very fast is because the faster solutions in the distributed RL setting actually get sampled a lot more frequently. So it sees a lot more gradient updates for those fast actions. So it's converges to the fast actions. So to actually counter that, we basically had a very simple algorithm where we just reweight the policy gradient update by the duration of the action. And we actually show in the paper, which you're welcome to check out. It's just called Reinforcement Learning for Machine Learning Engineering Agents. We actually show that, with this correction, we can get unbiased policy gradient estimates, which actually checks out. The math actually checks out. And then for the second issue of the sparse reward, what we did is basically we give the entire solution generated by the agent. But before we execute them in the code environment, we actually have an intermediate step, which we call environment instrumentation, which we use another copy of the model to insert a bunch of print statements. So you can see that we're going to actually keep track of the execution progress. And when we execute this code, then we can, in the trace, pass out where did the execution fail, right? And if the import package is printed, or if load data is printed, we're going to assign these intermediate partial credits to the agent. So it actually sees intermediate progress and tries to, learn to import packages first to get these partial credits, and one step at a time, right? So there is this intermediate dense reward information. It's very important to use a static copy of the model, because if we have the same model generate the print statement, the model might just learn to reward hack this partial credit by only generating print statement without actually, generating the code. But when we have a static model, we found that the model tend to not, hack the partial credits. So this is some promising results, right? So we took a very small model, which is this Quinn 2.53b, and we run this RL fine-tuning with our proposed improvements. We saw that as the time goes on, we can actually, for a very small model, to find better solutions than prompting Cloud 3.5 SONAP with this state-of-the-art agent scaffolds, right? I think this is, again, very interesting for academics to think about using RL to fine-tune small models as opposed to just prompting large models. And here are some effect study of the environment instrumentation, which is found with the environment instrumentation, sample complexity is a lot better. The model starts to make progress a lot faster than when we only have like final reward, which is the performance on the test split, because there's no intermediate signals for the agents to learn from. Okay, so I think the second part of the talk is relatively short, but the major takeaway is I think, just developing new RL algorithms, GRPO, PPO, XPO, right? Like it's only interesting in these new challenging settings where, for example, for MLE, right, we have variable duration actions. One action, trains the model for 10 epochs. One action trains the model for 1 epoch. How are we gonna balance the learning from these two drastically different amount of time executions, right? And if we just like naively have a synchronous framework stop the world, then that's not ideal because the efficiency is very low, right? But if we always just execute gradient updates on action that comes back the first, we're going to have this frequency bias, right? So these are the real interesting scenarios that we should be developing interesting RL algorithms or formulations even. For example, this continuous time discrete interventions could be formulated as a semi-MDP, right? Which is a concept that existed from a long time ago, but people sort of stopped considering those cases. People are more looking at MDPs where the time of actions are not taken into account. But I think maybe it's time to revisit those formulations, right? Because training the agent knowing when to kill its experiment, right? This continuous time discrete intervention is pretty much what we want for ML engineering. And then there's some additional information that I think are useful for like general agentic design, right? Which is like, if the interaction is going to be very expensive, how can we get as much information as possible from the environment, not just the reward, right? Because there are all of these traces, and even the traces themselves might not provide all of the information, right? So we can do these instrumentations like these print statements to try to get more information about, how is the agent performing, and so that we can get more we can utilize these expensive interactions better, right? Because we extracted more information. Okay, so that's on
Hey, Sherry, there's a
yeah,
question on the chat.
sure.
The question reads, will the agent run the CLI to verify this code after you do the prompting? That's the question about.
Running the CLI. I guess I didn't understand the question.
Just like the command line interface from your terminal. So after
Okay.
you do the like kind of like web coding for ask the agent to do the MLE coding.
Sorry. So after the agent does MLE coding, what are you proposing to run in the command line?
So for I don't really have a try like Codex like cloud code something. After you do the web coding, like somehow the agent may need to run the command line to maybe access those like the package you write for MLE code.
Yeah, those are great.
That,
Yeah, that's a great question. So in this case, we actually didn't give the agent access to the terminal, right? So I think, which is something to be considered. I think there's terminal bench, give access, to full access to whatever the agent wants to run. So for us, we just have an interpreter, so the agent could only execute code in that interpreter. But I agree that yes, we should have the agent be able to install packages, for example. So we have like a fixed set of packages, which is the case for MLE bench. It doesn't have like the agent doesn't have internet access. There are a lot of restrictions in these benchmarks. I don't think these restrictions have to be there. Maybe just for benchmarking purposes, they want to be fair, right? But I do think that yes, giving the agents more access to more tools will allow them to do better. Like they can just download some pre-trained BERT model, or some pre-trained LLMs and do stuff. Yeah.
I see. Thanks.
Yeah. Okay, so maybe due to the sake of time, let's move on to the last part of the talk. But I'm happy to chat more about the MLE agent if that's something more of you are interested in. So right. So I think for if you look at what people are doing in science, right? So like a lot of people are working on very domain-specific stuff, like developing some computational algorithms for computing some properties and so on. So those are very low level, right? So, but thinking about from like a language perspective, which is what this seminar is about, like I think one of the very useful tools for science will be this language to structure tool, which is, you input natural language, which is kind of like true for a lot of the LLM applications, which is you input some high level language, right? You can describe, as a material scientist, but not super, deep in the weeds. You want to just design some materials with some properties, with some specifications on the atoms and types, and like you want something new, right? You don't want something that already exists in the existing database. And then what at a high level we want is we want to use various tools like generative models, language models, diffusion models, predictive models, like given a structure, predict its energy, stability, analysis, and so on. And we want to get back like the most promising structure that follows this instruction, right? So I think this is something that the science people don't have. So you don't even have baselines because they don't have something from language to structure. So if you look at what people have done in like computational material science, they also try to do discovery, right? But like their method is very domain specific, where they use this ab initio random search, which is one of their tools. So what this tool does is it uses some algorithm to, given some initial composition formula, they would generate some initial guesses based on the volume. So they would randomly generate some structures with different kinds of volume, and then they're going to run this density function theory calculation, which is some kind of quantum mechanics based calculations to relax the structures to make them more low energy, right? And then after that, they can just choose based on some kind of ordering metric to get back a particular structure. But if you look at the issue with these computational methods is that the optimization they can do is pretty local. So, the structures they end up with is pretty similar to what their initial guesses were. And then the initial guess doesn't really have a lot of, rich knowledge in the sense of like internet scale knowledge, right? It's some kind of fixed algorithm. If it's some kind of organic material, we're gonna get some volume. If it's something else, we're gonna get some other volume. It's very, very heuristic based. And then again, there are a lot of high cost components, which is, we need experts to design formulas and, these guesses, and then running DFT is expensive. And sometimes after 24 hours, like 50% of the structure didn't actually converge, meaning like they didn't find a configuration that actually is a stable configuration for the material to exist. So this is the computational side, right? And if we think about what we can do on the learning side is actually there seem to be these two types of knowledge, right? There is the internet scale text data, which actually talk about materials a lot from textbooks, from Nature papers, and so on, from very front end research to, going 100 years back, like knowledge. They're all in the form of internet text. Maybe the missing part is like to complete this pipeline from language to structure, right, is this low-level structured databases, because these databases require some license and they're not in the internet pre-training data for language models. And because they're of a different modality, they're more like structured data, XYZ locations in the 3D space. So it's not super clear how we can get language models to be pre-trained on that. So as a result, there is a gap. So we can't just get direct language to structure from pre-trained LLMs. But nevertheless, I think there is some connection, which is formulas is actually one of the things that it connects both high-level knowledge and the low-level databases. And I think this is true for a lot of science domains because people need a way to identify the quantity they're talking about, right? So for the structures, they need some formulas to know, and then the formulas usually exist in the textbooks. So then what we propose in this generative hierarchical material search framework is we're going to take this language instruction, we're going to use some pre-trained LLMs to suggest some formulas that can follow this instruction. Of course, we can do some early pruning, right? For the structures, language model can make a lot of mistakes. So for the ones that didn't follow the instruction, we'll just filter them out. And for the ones that did follow instruction, we're going to give the formulas to a diffusion model that we trained. The diffusion model is trained to condition on formulas to generate the structures, because the low-level structure databases usually have formula information and structure information. So we can just, similar to how we train a text condition image generation model, right? So we just condition on the formula, generate the structure. And now what we have during inference, we have like this hierarchical search pipeline where we get a high-level language that actually narrows down the search space, right? And we get these low-level structures from the diffusion models, and then we can run these calculations and predictive models to get their properties and to do some further filtering. And so what we found is that this pipeline actually, through the diffusion model is actually a lot more effective in terms of finding the initial configurations of materials that can converge during the DFT relaxation, right? So the thing is, after the diffusion model proposed the structures, we can further relax them using DFT, but we want the DFT to have a high convergence rate, right? So this is a comparison where AIRS is what people use traditionally in computational material science, and then UNIMAT is what we use to generate the structures using a diffusion model. We found that the convergence rate is much higher for a generative model, conditional on some novel formulas. And we also found that the energy, in general, lower energy, the better, because we want stable materials. We found that the structures proposed by the generative model is also oftentimes of lower energy than the structures proposed by computational material science, tools from computational material science. So I think something that's even more interesting is the idea of scaling up inference time compute actually applies to science as well. When we try to generate multiple language branches per initial instruction and increase the number of structures we generate per language, we could always find materials of even lower energy, right? So we're turning something very computationally or expensive from DFT or from real world labs, but then just changing them into running inference for language and diffusion models. So I think this is worth pointing out, where we actually were able to collaborate with experimentalists. So Omar Yaghi actually recently won Nobel Prize for his discovery of moths. Not for this work, because this work is pretty recent, but he's working on ways to discover moths for a long time, and now AI is just a tool for him to discover moths that he has yet to discover. And so we have some AI generated moth structures on the left. MOF stands for metal organic framework, so it's half organic, half inorganic. It's connected by organic linkers, and these materials have nice properties for storage purposes and so on. So so if you look at these structures, like on the left is generated by this pipeline using language to suggest formulas, diffusion to suggest structures, and some properties to do filtering. On the right is are what were synthesized by this wet lab. And this current paper is under submission to top tier journals. So I think this is one of the things I'm the most excited about because it's really AI put in real science. So I think one of the things that is worth mentioning is why do we want to do discovery with generative models? I think the concept of generalization or combinatorial generalization really applies here for metal organic frameworks, right? So for example, for text to image generation, you have images of astronauts, image of horses, and now you have some other images of like a kid riding a horse, right? And then you learn the relationship of riding, and then you can generate a image of an astronaut riding horses, which is unrealistic, but it could exist, right? Like which is highly realistic, right? And so similarly, I think in the past, subjects in science are divided into different disciplines because people think they're unrelated. So you have organic side of things and inorganic side of things, and data are different. Data, like communities, are different. In the past, people probably wouldn't talk that much across communities, but when you actually want to do things that are cross types, like for example, you want to create materials that are half organic and half inorganic because they have special properties, you actually want data from both, right? So I think this is where we, as machine learning AI people, can come in and actually tell them, like, you can train a single model across diverse data sets and get back something very interesting in terms of compositionality, where similar to how you compose astronaut riding horses, and now you can compose, because astronaut riding horses is in the text, and then the relationship between atoms is also in the formula, right? Like what composes with what. And now you have a new formula, which is a new way of composing atoms. And you can actually, get something very similar to astronaut riding horses, but in a structure space. So yeah, to sum up, I think the last part of the talk is, we talked about, trying to synthesize things is expensive. But I just want to say, like, any kind of human knowledge should be reusable. So any kind of expert knowledge that goes into the design process of discovering a material, those data could go back to the LLM to, have them be more like a scientist. I think a lot of people are working on this so that we can reuse human knowledge, right? We don't have to ask domain expert to always design formulas for us. We can ask LLMs to propose formulas. So this is one way we can, really cut down the cost, which is because for science, oftentimes the cost is humans. Another is, the space for discovery is really vast, but I think like language or formulas really gives us a way to effectively narrow down the search space to, directly target things that are more promising, which is exactly how we can, find these moths in a very short period of time. So with that, I think like I want to, just spend a couple of minutes, right, to chat about, we did seem to discuss these three very different domains, and we talked about very different things like world models, reinforcement learning, and system of agents. So exactly, are there any commonalities across these three topics? And I think the answer is yes, right? So for example, I think world models not only apply for robotics, they also apply for other high-cost environments, for example, engineering and science, right? So for example, what is a world model for engineering MLE look like? Well, we could have models of cost. Okay, how long is this experiment going to take, right? So if we have a model for that, we can decide which experiments to run. And model of information, right? So what could be the training loss if I were to run this model without actually running the model, right? And if we can get those information, we don't have to actually run experiments. And it's the same concept as world model for robotics, where you don't have to move the robots to know what happens. And similarly, developing world model for science, right? So this is one of the examples where people will have to run like molecular dynamic simulations using, quantum physics to be able to kind of like simulate some long time scale properties of some structures. And this is really expensive to run. And it also, when you have like a really large system, right, when you have a lot of atoms, it becomes like almost impossibly expensive to compute for very long dynamics. But remember, like the lesson from the world model is like you can actually skip frames, right? You don't have to model every frame. You can learn that dynamics model that allows you to kind of like, generate course frames into the future and kind of knows what happens. So I think like world models on molecular dynamics data or on just any kind of scientific dynamics data also have a lot of values. And they don't have to scale with the number of atoms, right? We can have various representations to save the complexity. Another connection across these three different domains is that you kind of already saw these plots maybe for the second and third part of the talk, where all three domains actually touch on some notion of abstractions, right? Where you probably have some high-level language plans. For MLE, you have high-level language plans, low-level code, and you want to, potentially, so for RL, right, like it's actually optimizing both the high-level plan and the low-level code. But you can also, when you apply some, search on top of it, you can, always find good high-level plans before find good low-level code and so on. So the concept, and similarly for agents, where we for the science agents, where we generate formulas first before generating structures to narrow down the search space for good solutions, right? And for the first part, I didn't really show you this video, but the point is like you can actually generate sub steps of completing tasks using language models, and then you can generate the videos for completing these tasks to select, which branch to take, and then you can translate those successful branches into the action space to be executed in the real world. So this is called video language planning. You can also check out this work. So, but the point is that even across different domains, the notion of world models can be shared. The notion of having hierarchies and search through hierarchies and plan through hierarchies, or doing reinforcement learning across hierarchies, is also pretty much a common theme. And maybe lastly, when we look across these dimensions of developing world models, developing agents, and developing science, we can really develop, these maybe, science robots, physical agents that can do scientific experiments, clean your labs, putting petri dishes to the places they should be put. Right now, I mean, there are some very simple setups like that, but usually it's hard programmed routines, right? Like the robot will just move left, right, because a general purpose robots is a little harder to achieve. Like you have your petri dish being different colors and being able to generalize to arbitrary locations. But eventually, yeah, because we're getting there, right? So maybe eventually we can have actually these physical agents for science to further speed up. We don't have to have humans to make materials. We can just automate that process. Yeah, so with that, I would like to thank a lot of my collaborators, including some of my own students at NYU, and also across industry and academia, and also many PIs across different universities I've worked with. And with that, thank you for your attention, and I'm happy to take any questions.
Thank you so much. This was a great talk. let's take one or two questions right now, before we break out.
I have a quick question, Sherry. Very, very interesting talk, very inspiring. I think we're also, from the language side, always thinking about higher level planning. Particularly, for example, I work on narratives, and then also some other like reasoning even. I think for some of the environment, like the robot environment that you have, it seems it's kind of easier to have that higher level planning in terms of like go left, go right, or grab a how to say grab a table, oh, sorry, grab a cup and all that.
Yeah.
But in language, for example, our high level plan, I would imagine in the reasoning trace would be that I want to first break this down, and then I want to do some calculation, and I want to do some inductive reasoning, and I want to do some deductive reasoning. And those are sort of all hidden labels that we know, it's latent variables that we know it's going, that's what's going on. But what we observe is just a token based, like a word level thing. I wonder whether you have been thinking about this, or like how some of these higher level plan um, uh, would be transferable to pure language based reasoning. And similar, like for AI for science, if we're thinking about like mathematical science, mathematical proof, like it, yeah, like the
Yeah, yeah,
level.
yeah. I think I understand your question. I think it's very interesting to hear that because, like, for us, we were always jealous of people working on language because you can just represent, high level actions, low level actions, all use the same data modality, right? Like for us, the cut is clear wherever the modality boundary is, right? Like when we go to like the robot actions versus when we're, doing language, and same for science when we're talking about XYZ structures versus high level properties or high level descriptions. So, but then there's no gradient flow, right? Like when we actually switch models because of these lack of multimodal supports and so on. So we were actually always very jealous of language people who you can just like do both high level and low level, in the same trace. You just tell the model to come up with a low level, high level plan before come up with low level execution. The model can just follow it. But I guess I see your point about maybe the boundary is just less clear. Like what is the high level plan? Like when do you switch to, the low level mode? For us it's a lot cleaner. What is the interface? Like for science it's formulas, for robots it's like some kind of language and
Actions, I
yeah,
think, like
actually,
one
exactly.
word.
So yeah, I think maybe, I mean, one intuition I have developed is thinking about more from the perspective of getting reward information, because I think for a lot of different RL algorithms or planning or search, it's really about knowing something about the future, and then optimizing some current decision. I think maybe in the text setting, it will be like knowing something about the low level to be able to optimize something high level. So, and I think in those cases, like we can actually traverse for text, I guess it's this abstraction space, but for robots or for science, it's kind of like the time dimension by using something very abstract. Like for robots, right, we can, have something like a video, just like very coarse grain telling us grasping the banana. And immediately we know whether that's a good task to do, good first step, if the goal is to put everything in the top drawer, for example. So I think maybe similar for language, I think is like, especially if we're thinking about like reinforcement learning or learning from feedback, is like we can think about credit assignment for these high level. At what point does it make sense to think about credit assignment for a high level strategy? There is enough signals for that. Like I don't know if that makes sense. Like I think the definition for maybe the interface of the high level and the low level is basically I have enough information at that level to tell whether that abstraction is good or not, and that is sort of like a natural natural split of this hierarchy is my best guess, because that's like where the branches will happen. That's where RL learning the value functions will happen, and thinking about what are kind of like those branches is probably my best guess. Yeah.
Right. Okay, thank you. Yeah, this is helpful. Actually, maybe if no one else is asking, I have a follow-up question. I think it's actually associated, and I might miss some of the details in your first work. You're talking about training using videos, right? Sort of, you have a previous frame, and there will be an action, and there will be a next frame. But I think it's actually a similar problem as language in the sense that it is completely continuous. Um, Whereas you actually need to pick the right frame to say, this is the previous frame. And then I move something and then I ended up in a next frame and you need to pick it. It doesn't seem to me that you can actually just randomly pick a like time interval or whatever to define your previous frame and the next frame so that it can serve your purpose. I wonder whether there are some design choice that went into that, or there are some data set that's already like basically whether the data set is already available or there are some design choice went into the preparation.
Yeah, that's a really good question. I think maybe the short answer is like world model is not there yet to really consider what we should put in the context, because there's some assumptions about the world is Markovian. Like if I have the current frame, I don't need anything else. But this assumption is clearly false, right? Because like if the task is to find some objects that's in the drawer, right? If it's not in the context, like the world model wouldn't know there is object in the drawer. And given that image tokens actually take up more space than text tokens, and right now, like how can we store long-term memory about the environment in the context of the world model, so that when we actually give the world model action opening the top drawer, we can see the object that was actually put into the top drawer, right? That probably will require us to actually do retrieval, or like understanding that, okay, at some point in time, the object was actually put into the drawer. Like in some kind of, maybe we can use language to summarize, what happened, to maybe save things more compactly, right? Or maybe we just need like somehow retrieve the frame and that captures that information to be able to simulate opening the drawer properly with the right object inside. So this is completely like an open area for world models, where the world models don't have very long-term memory, and it's not super clear how to, because naively scaling up the context length, even if we have 1 million contexts, which is what language models have, like it's impossible for us to store things that was put there like 3 days ago. So it's definitely like an open question for how do we select proper context so that world models can have memory.
Okay.
Awesome.
Thank you.
Yeah, it's a really good question that we don't have answers for right now. Yeah.
Cool. Awesome. Let's thank our speaker once again as we come to an end for the talk. Thank you so much.
Yeah, thank you.
And yeah, I think we'll use the same Zoom room, Sherry, for the student chat. So we have like 3 student chats starting at 3:30. So we have like a
Okay.
25-minute break now, and then we have like 3 30-minute sessions after that.
Okay, sounds good. Yeah, I'll talk to the students. Looking forward. Yeah,
Awesome.
thanks a lot.
Thanks so
All right,
much,
thanks
and
everyone
have a great talk.
for
Yeah,
your
thank you.